one final example of being able to do an implicit derivative and then also utilizing it is we want to find an equation of a tangent line to the curve y cubed plus 3x squared y equals 140 at the point 1, 5. So this basically entails almost everything that we've seen so far with respect to implicit differentiation. So let's start by finding our derivative, because to find an equation of a tangent line, we clearly need the slope, and the slope is just going to be dy dx. Rise over 1, change in y over change in x. So, excuse me, we're going to go ahead and find the derivative of this y, which is 3y squared. For this term, this 3x squared y, this is a product rule. So what we're going to do off to the side is we're going to define little f to be 3x squared. We're going to define little y, or little g, excuse me, to be y. And the derivative is going to be 6x, and the derivative of y is 1. Right. Now, what we're also going to do is we're going to remember that anytime we take a derivative with respect to y, we have to multiply by a dy dx, and we have to do that over here as well. Right? So we have 3y squared dy dx. We're going to use our product rule, f prime g, fg prime. So that's going to be plus 6xy, and then 3x squared times dy dx. And I'm going to erase all this stuff so that way we have some room to work. So we have this 3x squared dy dx, and the derivative of 140 is 0. Now we're going to go ahead. We're going to take the 6xy to the right-hand side because we want to isolate dy dx terms. So we get 3y squared dy dx plus 3x squared dy dx is equal to minus 6xy. We have to solve for dy dx. So notice there's a common factor of dy dx. So we're going to factor that out. And if we factor out dy dx, we're going to be left with 3y squared plus 3x squared equals negative 6xy. And two ways to write the solution to this, at least for the slope. We could say that dy dx is going to be equal to the opposite of 6xy over 3y squared plus 3x squared. Another thing we could do that might make our lives a little bit easier is in the denominator, notice that we have a factor of 3 and a factor of 3, so we can go ahead and factor those 3's out. And notice that there's a 6 and a 3, so we can simplify that. So another way to write this would be the opposite of 2xy divided by y squared plus x squared, or x squared plus y squared. Right. Now this is probably the most simplistic way that we can write the slope. Okay, so remember dy dx, which is equal to m, which is equal to the slope. But we're not interested in just the slope, we're interested in slope at a specific point, which in this case is 1, 5. So let's go ahead and substitute. So now we're going to evaluate dy dx at the point 1, 5. Is going to be equal to the opposite of 2 times 1 times 5 divided by 1 squared plus 5 squared. And by computation, that's going to be the opposite of 10 over 26, or in other words, negative 5/13. And that's our slope. Right? So let's hold on to that. We know that x1 is 1. And we know that y1 is going to be 5. So now we can go through and equate our formula for the equation of the tangent line. So remember, we have y minus y1 equals mx minus x1. So y minus 5 is going to be equal to not the nicest slope that we've seen so far, negative 5/13 x minus 1. We're going to distribute, and we're going to get negative 5/13 x plus 5/13. And then the last thing we're going to do is we're going to add 5 to both sides. So plus 5, 13ths plus 5. Now to get this, all right, we don't want the decimal. All right, I know it's easy to stick it into the calculator and get a decimal, but let me show you what to do with this so that way my math lab does not reject your answer. What you're going to do is you're going to type in 5/13 plus 5 and hit enter. Now you're not going to enter this decimal. What you're going to do is you're going to hit math, and then you're going to hit enter, and then enter, and it gives you the fraction right here on your calculator. All right, that's what my math lab wants. It wants it in a fraction or an exact form. Right? So our equation of our tangent line finally is going to be y equals -5/13 x plus 70/13. All right, now, how do we know if this has any sort of semblance of validity? Well, what we're going to do is we're going to go ahead and graph it. So let's go over to our grapher, and we're going to type in both the original function, which was, I believe, I cube. And by the way, to get to this grapher, look at the previous video towards the end, and I show you the website as to how to get to the Desmos implicit function grapher, right? It should be implicit relation grapher. So this is going to be plus 3x squared y, and that's equal to 140. All right, and here's the graph. And almost for those of you that have suffered through statistics, it looks similar to a normal distribution. All right, it's not clearly by some of the characteristics of the standard normal distribution. It's not. And for our answer, we're hoping that at the point 1, 5 that we have a tangent line. So let's see what happens. So we get y equals -5/13 x. That doesn't look good. Plus 70/13. All right, so that looks pretty good. Now let's zoom in at the point 5 or 1, 5. All right, so right here is 1, 5 is right here. So this looks like a pretty good tangent line. Let's see how good it is. So we're going to zoom in. We're going to zoom in. We're going to zoom in. Oh, it looks really good. And remember, one of the true tests of the tangent line is if you zoom in, it starts to actually meld into the original function. So we shouldn't see like any gap between the line and the curve. Right? So let's zoom in a few more times. And again, we're looking at the point 5, 1. So here's 5 and here's 1. We can tell it right down here. So it looks like it's really close. And as we keep zooming in to the point 5, 1, so here's our 5 and 1 here. As we keep zooming in, there's no more orange. It just stays in this navy blue color. All right, so that means that the function, the original function and the tangent line are kind of sitting on top of one another so closely that they almost represent one another. All right, and that's good because I'd much rather work with this linear function, even though it has the fractions in it, than this function right here, which isn't even a function, excuse me, this relation right here. All right, so if I'm a programmer or if I'm somebody that's working with mathematics and I want to try to use a computer to represent the behavior of this relation, I might use a linear approximation to do that. And just as a reminder, linear functions are much cheaper a lot of times with respect to memory and RAM than some of these other types of more expensive functions, especially this one that's not even a function. Right. So hopefully these videos help you to be able to get an idea as to why we need implicit differentiation, what implicit differentiation is, and the techniques to be able to find an implicit derivative.